Thank you. It's a pleasure to be giving you today an update on the first Galaxies project results. So today's talk, I will first present our most recent results on galaxies at cosmic dawn with the Hubble Space Telescope. We'll then move on to provide some modeling and interpretation that we carried out in the project, focusing in particular on stochasticity in star formation to interpret the Hubble results. And I will conclude with a future outlook covering both JWST preparation plans as well as smaller sibling space telescopes. So to find first galaxies due to their faintness and rarity, a large investment of telescopes such as the Hubble is needed for multi-band imaging surveys to carry out approximate color selection techniques, essentially to find tiny red dots in a haystack of foreground galaxies. And in particular, in our team with ASTRO 3D research fellow Michele, we focused in the last year and a half or so on identifying galaxies brighter than the Milky Way, so brighter than L-star galaxies, using the Superborg compilation of imaging, which is the largest area survey available to date with Hubble to find these rare objects in the epoch of radionization. And Michele has very interestingly found that there seems to be an excess at the bright end compared to earlier determination of the galaxy luminosity function at these redshifts. This is very intriguing. We'll learn more with it with JWST. But of course, because these are photometric candidates, it's very important to estimate carefully what's the probability that our samples contains interlopers. And this is in particular a project that we started with a new PhD student, Hilmi, and Nietzsche, where we are looking at how we can use innovatively the cross-correlation of Lyman Bray galaxies at high redshift and interlopers at intermediate redshift to infer information on our sample purity. And here in this plot, I'm showing some of the theoretical results that Hilmi is finding using the theoretical astrophysical observatory framework by simulating a cross-correlation between these two samples. And we see that as we increase the leakage fraction from one sample to the other, we get a clear signal in the cross-correlation. So we'll now soon apply those to actual data. Another way to gather some extra information on these bright rare galaxies at cosmic dawn is to combine Hubble with Spitzer observations. And Spitzer was able to observe a good fraction of the brightest galaxies in Borg. And here I'm showing one SED fitting combining Hubble rest frame UV with Spitzer rest frame optical data that we had on one of our very bright galaxies, 25th magnitude photometric redshift 7.6, giving us a glimpse of what are the properties of these galaxies. So overall, Hubble counts well sources, but those are fuzzy blobs. So many open questions remain. What's the luminosity function at redshift greater than 8? Is it shatter? Is there this excess? What are the properties of these sources? Particular, how efficient is star formation? How does chemical enrichment proceed? And so one way of making some progress with current data is to use innovatively gamma ray burst as probes of the interstellar medium in their host galaxies. And this is a line of investigation that we are carrying out with PhD student Ben Mehta. Using hydrodynamical simulations, we are looking at the relationship between absorption and emission metallicities in GRB host galaxies. At the moment, there is only one host galaxy with this type of data, but with JWST in cycle 1, we expect to have 10 to 15 objects observed based on approved programs that will give us data good enough, hopefully, to constrain subgrid recipes in hydrodynamical simulation to understand how the early metal enrichment proceeds in these sources. Another approach to study the inhomogeneities in these early forming galaxies that Ben is introducing is to use geostatistical tools to go beyond uniform metallicity and modeling or radial gradients using universal kriging and semi-variograms. And the power of a geostatistical approach is illustrated here in this plot that shows predicted metallicities versus the measured metallicities from a local galaxy that we analyzed in collaboration with the Typhoon team. And you can see on the left how the geostatistical model is much more accurate than a gradient-only representation for multiple metallicity indicators. If we consider stochasticity rather than internal to a galaxy as an ensemble of galaxies, then we can also use these as a tool to investigate what are the expected clustering properties around bright quasars at the end of the epoch of reionization. This is work that former PhD student in the team recently completed, Kevin Wren, and Kevin showed how from cosmological simulations, after taking into account stochasticity in the efficiency of star formation, one gets a variety of environments in terms of clustering properties around the bright quasars at redshift 6, explaining the recent observations that show lack of strong clustering around these sources. Kevin, also using a similar model, studied how dark matter halo assembly can be used as a driver for the evolution of the quasar luminosity function. And we built a simple model that calibrated at one redshift, redshift 4, gives us a good evolution of the quasar luminosity function at redshift 5 and 6, and makes interesting predictions on the abundance of these accreting black holes at redshift 8 and beyond. And with the Borg collaboration, in particular with Takahiro Morishita, we are now setting some limits on searching for point-like sources in the Hubble data. The future, of course, will be extremely bright, and in particular, beyond the 2-micron range, we'll have amazing data with JWST and transformational results very, very soon. In particular, with Nietzsche and the GLASS JWST ERS team, we are preparing to have the first look at the rest frame optical properties of epoch of reionization galaxies using what could be the very first NIRCam data that JWST will take for science in early July. Another very interesting approach with JWST is to follow up the bright galaxies that we discovered with Hubble for spectroscopic studies. In particular, the bright galaxies that we have in Borg can all give us good spectra that go down to the continuum. I see a variety of metallicity lines with just a few hours of observations of NIRSpec or NIRIS. And we have programs approved for dedicated follow-up of Borg sources on with NIRSpec, and with the new First Galaxies research fellow Kit Boyett, will also use the NIRIS blank pointing to discover new redshift 8 sources and characterize their continuum and their emission and absorption lines. And finally, I would like to spend a minute talking about ways to complement these flagship observatories such as Hubble and the GWST with advanced instrumentation on nanosatellites. And as lead of the SPIRIT nanosatellite, I feel very privileged to have been selected to lead the first mission of the Australian Space Agency. SPIRIT is only a 12-kilo satellite, so it's a shoebox-sized satellite, but it's equipped with an advanced gamma and X-ray instrument, which is being built in Italy with funding from the Italian Space Agency. And the HERMES instrument that will fly on Spirit will have a sensitivity comparable to the Fermi gamma burst monitor instrument, which is on a satellite or on a class of cost which is 1 to 2 orders of magnitude greater than the Spirit HERMES project. And with this innovative instrument, we are expecting to be able to detect gamma ray burst at cosmic dawn, as well as localize gravitational wave counterparts from their short GRBs. Spirit will innovatively cool the HERMES instrument and serve as a technology demonstrator for thermal control that could enable future infrared space telescopes on a similar class of nanosatellites. And we are doing this project in collaboration with multiple Australian companies. So we are growing Australia's space industry and strengthening collaboration between academia and industry. The Spirit science cases are inherited from the HERMES instrument and HERMES constellation of the funded in Italy and in Europe. HERMES stand for high energy modular ensemble of satellites, and will use time of arrival of photons to localize in the sky high energy transients. Both long GRBs at cosmic dawn and gravitational wave counterparts will characterize fast variability of the GRB inner engine and possibly even granular structure of space-time. So new collaborations, especially here in Italy, here in Australia, are very much welcome. So here is my summary. Hubble transformed our view of cosmic dawn, and the future is very bright with GWST and smaller space telescope siblings, and the first Galaxies team is ready to take advantage of these facilities.
Thank you, Michele.